Hi, this is Peter with CalcBook, and today we're going to be looking at a timber column design using sawn lumber. So just as a quick recap, right, we are using the National Design Specification, also known as the NDS, and there's two books that we use. It's the NDS spec and then also the NDS supplement, both of the 2018 version. So for the specification, right, that gives us our design procedure, capacity equations, our adjustment factors for, the general equations for load duration and things like that. And then we have section 3.3 for flexure, 3.4 for shear, 3.5 for deflection, 3.6 for compression, and then 3.9 for combined loading. And then the supplement gives us our reference design values, shape properties, geometry, section properties, and then any specific adjustment factors for the species or type or type of lumber that we're looking at. So for today's example, we're going to be looking at compression, right? So we're going to be utilizing our F prime C equation, which is up there on the top there with many different factors that we have to calculate and apply. The most complicated or tedious is going to be the buckling factor, that column stability factor, CP, and so we will calculate that in CalcBook. So let's take a look at our problem statement. Right, we're going to be doing a column design. It supports a floor beam. So there we've got our red floor beam there with the orange column. The floor beam goes right over the top of the column. We've got a column length of 8.25 feet. We're going to be using a Douglas fir larch species, and then our size, we want a 4x, just because that is the size of the beam going over the top, so it makes it for an easy connection. Our loading comes from above, right? We've got some different loading here, but we've got a calculated dead load of 2,250 pounds and a calculated live load of 3,750 pounds, and we're going to be using ASD. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we'll go ahead and click into our timber design module, and then we'll go ahead and click into our timber member design, and we're just going to be looking at axial, so we can just click on axial and click confirm. Okay, so we go ahead and select our lumber type. Depending on the size, you would either select a post and timber or a visually graded lumber, and since we're going to be starting with a 4x, we're going to go with visually graded. Posts and timbers are for 5 inches and above, so we'll start with visually graded. Dimensional lumber. Our species we said is Douglas fir larch, and then our grade was optional. We're just going to go with not optional, it was not defined, but we're going to go with number 2. That's a pretty commonly available grade for Douglas fir larch for a 4x4 post. And then our size we said was going to be a 4x, and we'll just go with a 4x4. That's a pretty standard size for a column of supporting this type of beam. So we've got our member selected there. Next thing we want to do is go ahead and switch over to ASD. So change our settings to ASD. Click confirm. Our load duration factor, right, we want to use 1 again. That's going to be the dead plus live using our occupancy live load. So we'll change that to 1. And then our moisture content, temperature condition, leave those as is. This is a not incised member, and it is not repetitive, so we'll leave those unchecked. Okay, now we can toggle over to our axial design. And we need to adjust some things here. So our unbraced length we said is 8.25 feet, which is 99 inches. And that's going to be both the X and the Y axis. And then our effective length factor, right, we've done this before with steel. We're just going to leave it as a 1.0 for both the X and Y direction. Then we need to enter in our demands. So we have a dead load of 2.25 kips and a live load of 3.75 kips. Perfect. And we've got a DC ratio here of 0.91 that we can see, so that is good. And now we can go through and just check and confirm some of the design options. So let's look at our compression stress, right? We have our P over A of equations, so we have 6 kips over the area of the member, which is 12.25 inches squared. And that 6 kips comes from our load combination, just D plus L. Right, then we get into the actual compression calculations. So we have our various adjustment factors, right? So we have our load duration. Our moisture content is less than 19%, so that's 1. Same thing for the wet surface factor for modulus elasticity is also 1. Our 4x4 grade number 2, so we have a shape factor, size factor that we have to apply, which is going to be 1.15. Not incised, and so that's going to be a 1.0. And then we have the sort of the meat of the problem here, calculating the stability factor. So we have our KL over X, our KL over D and our KL over B for each of the directions, the slenderness ratios in each direction. And then we take the minimum of those. In this case, it's going to be the same because it's a 4x4 member and its unbraced lengths are the same about both axes. We calculate our adjusted modulus elasticity for the column stability equation, and then we have our FC star, right? And that's basically the compression equation, but with the CP factor, the stability factor, removed. We calculate our critical buckling value. We have our constant C for sawn lumber, and then we have our big equation for the column stability factor C sub P. And we get that we have a C sub P of 0.35, so quite a bit of reduction here on this column. Then we calculate our FC prime equation, right, which is the same thing as FC star, but now we do include our CP factor, and we have our low duration factor in there, and that gets a DC ratio of 0.91. So that is a column design for sawn lumber in CalcBook. We hope you enjoyed the video. If you have questions or suggestions for other designs, please let us know in the comments below, and we'll see you next time.